Hey guys, Mr. Betts here. In the last topic, we talked about the fundamental theorem of calculus and how we can use it to evaluate definite integrals. And part of that process involved antiderivatives. So looking for functions that we take the derivative of to get the function we're taking the area of. We're going to start the journey of finding antiderivatives for different types of functions. And all of the processes that we're going to talk about are going to be based on how we got those derivatives to begin with. So basically, in other words, everything that we're going to talk about is going to come from our differentiation rules. So first of all, I want to talk about some notational stuff. So this notation right here, notice that it uses the integral symbol. I'll talk more about that in a second. It's called an indefinite integral, and it can be expressed like this, where the derivative of big F is little f. So essentially, this is saying, what do we take the derivative of to get this? Also, a notational thing here, I don't have it on the slide, but this inside part of the integral is called the integrand. It's a word that I've used off and on while we're talking about integrals. So the integrand is just the inside of the integral, just like the radicand is the inside of a radical. So if you hear me use that word, you know what that means. So notice also that it has this plus c, that constant of integration. So a few examples here. If we take the derivative of x cubed, we get 3x squared. So the integral, or the antiderivative of 3x squared, is x cubed plus c. Because if we replace this c with any constant, the derivative of that constant is going to drop out. So notice that all of the ones that I have here are derivative rules that we've talked about. We take the derivative of a polynomial by using the power rule. Well, we can undo that power rule, and we'll talk about that in a minute, and work in the reverse direction. The derivative of the sine function is cosine. So we see an antiderivative like this, and we think to ourselves, what did we take the derivative of to get cosine? What do we take the derivative of to get 1 over x? And that would be the natural log of x. I do want to point out that this works only for positive x values, because we cannot take the natural log of a negative value. Remember that the natural log is the inverse of the exponential function, and e to the x is always positive, which means that the natural log of x can only take positive values. So this definition here, this antiderivative, only works when x is positive. Before I move on, I do want to point out that the symbol that we're using here is the definite integral symbol without the limits. So we don't have the a and the b, or the 0 and 2, or whatever it is here. So it's the same symbol, but the fact that they're connected is only due to the fundamental theorem of calculus. The antiderivative and the area problem are not necessarily related to each other, except that we have this fundamental theorem of calculus that does connect them. So we are using the same symbol for two different things. If we have limits, it represents an area. If we don't have limits, it represents an antiderivative. They are connected with the fundamental theorem of calculus, which is why we use the same symbol, but I don't want you to think that that means that they are essentially the same thing, because they are not. So again, if we have the limits, that is an area defined by a Riemann sum. If it does not have the limits, that is an antiderivative, or what do we take the derivative of to get the integrand? This is also known as an indefinite integral, where this was a definite integral. I like the term antiderivative better, because it's descriptive of what it actually does, but indefinite integral is accepted. And just keep in mind that it means something different than the definite integral, even though we use it to get the definite integral. So I mentioned this already, but the differentiation rules that we have talked about are going to be the foundation for finding antiderivatives. We're just going to use them in reverse. So some of the rules are easier to reverse than others. So I'm going to start with the power rule here. This is one that's fairly straightforward to reverse. So just as a refresher, if we're taking the derivative of x to the k, that k goes out front. and then we decrease the exponent by 1. So for example, the derivative of 12 or x to the 12th power is 12x to the 11th. To reverse it, we're going to reverse it, and we also have to reverse the order that we do it. So we're going to increase the power by 1, and then we're going to divide by the new power. Okay, so where we multiplied by the exponent and then decrease the power by 1, now we're going to increase the power by 1 and then divide by the new exponent. And then keep in mind, anytime we are doing an antiderivative, we need that constant of integration. So this right here is the power rule that we're going to use for antiderivatives. If we look at trigonometric antiderivatives, I'm going to start with what is the easiest one on this list, and that's the cosine one, actually, because we know that we take the derivative of sine of x to get cosine of x. So the antiderivative of cosine is sine plus c. The derivative of cosine is the opposite of sine of x. So reversing that, that negative here, if I just do this, then we can reverse that and say that the antiderivative of sine of x is the opposite of cosine of x. Now, before I go any further, I just want to mention that this is something that is very, very commonly missed, because now that we're doing antiderivatives, the rules are flipped. So when we took the derivative of sine, that's cosine. Now when we take the antiderivative of sine, it's going to be the opposite of cosine. So we need to be careful and think to ourselves, what do we take the derivative of to get it? So always try to think in reverse. What do I take the derivative of to get this integrand here? If you think of it that way, it should help you get it straight. I do also want to mention before I move on that you can always check your answer by just taking the derivative of that and see if we get that. And if you don't, you might have to manipulate it a little bit. Tangent and cotangent and secant and cosecant are actually ones that we can't take the antiderivative of yet, knowing what we know, because there are no derivative rules that say we take the derivative of something to get tangent. We have derivative rules for, say, if we take the derivative of tangent, we get something. Hopefully you know what that is, but if you don't, it's time to start memorizing those. So these we are not going to do yet. We will do those later. So if we think of what we do get when we take the derivatives of the trig functions, I have those listed here. So hopefully you were thinking to yourself that when we take the derivative of tangent, we get secant squared, which means that the antiderivative of secant squared is tangent of x. Now, cosecant squared, remember the derivative of cotangent is negative cosecant squared of x. So if I want to apply that here, then the derivative of the opposite of cotangent is going to be the opposite of negative cosecant squared, or just cosecant squared. So this is going to be the opposite of cotangent of x. The derivative of secant is secant times tangent. So this is going to be the secant of x plus c. And then just like we had to here with the cotangent rule, this is going to be the opposite of cosecant. Okay, so just reversing the trig derivatives to get antiderivatives, these are essentially the formulas that we are going to use for those. Exponentials and logs. So remember, the derivative of e to the x is e to the x. So this is going to be one of the easiest ones, plus c. The 1 over x I have here because the derivative of natural log of x is 1 over x. I mentioned this already in this video, but this only works for x values greater than 0. If I want to, and we should be able to, let x be negative, then we can use some properties of the 1 over x function. And I'm going to talk more about this in another video. But essentially, what we can do is we can say that it's the natural log of the absolute value of x. These absolute values are very, very important. If you don't have the absolute values there, then the antiderivative is not accurate. It's not right, because we do need to allow x to be negative here, which means that we need to allow x to be negative here. Now, just putting the absolute values in there allows x to be negative and then makes it positive. The properties of 1 over x is what allows us to do that. And like I said, I'll talk more about that in another video. The derivative of a to the x is a to the x times the natural log of a. And keep in mind that the natural log of a is a constant. Let's see if I can spell that right. So reversing this, I can divide by that constant because we have a constant multiple rule, and divide by the constant here. And so the antiderivative of a to the x is going to be a to the x over the natural log of a. So this last one on here, I put on here because I wanted to show you that we don't actually need it. We don't need to reverse like we did here, this rule. So first of all, the derivative of a log with another base is 1 over x times the natural log of b. So if we're trying to reverse this one, we can actually reverse it using this rule right here. Because that natural log of b is a constant, we have a constant multiple rule for antiderivatives, just like we have for derivatives, because we're reversing derivative rules. So we don't need a new rule to reverse this. I also want to point out, like I talked about with the tangent function, this is one that we cannot do with the tools that we have right now. We can't say, what do we take the derivative of to get a log? We actually can't do that with the natural log either. We don't know what the antiderivative of the natural log of x is using the tools that we have right now. So again, I'm going to put not yet. So the ones that you need to be familiar with are going to be these right here.